an ancient, otherworldly visitor is hurtling toward our sun. And for a month now, the world's most powerful observatories have recorded a single supernatural point of light. Each new glimpse has only deepened the mystery instead of solving it. Soon time is running out. The object will slip into the sun's glare and disappear from view, leaving us with unanswered questions. What is it? Officially nicknamed 3I/ATLAS, the third interstellar object. It appears to have originated far beyond our own solar system, somewhere among the countless stars we see at night. We don't know its home sun, but evidence points to a very ancient birthplace in the Milky Way, possibly from a system twice as old as our own. It is only the third interstellar wanderer humanity has ever seen. First came Oumuamua, a strangely elongated body that swept past in 2017 and defied easy explanation. Preliminary data suggests 3I/ATLAS may be even stranger. Then came 2I/Borisov, an overlooked average cometary object. It looked and behaved like a typical comet, just a comet orbiting another star. 3I/ATLAS, however, promises to be our best chance of studying a truly unusual alien visitor. And it's one of those cases where every new data point makes the story even stranger. The object was first detected on July 1st, 2025 by the Asteroid and Earth Impact Alert System, ATLAS, hence the name. Later analysis shows that 3I/ATLAS first slipped into view on May 7, 2025 in frames from NASA's TESS. The spacecraft was then focused on its exoplanet hunt, so the newcomer was not flagged. In that early image, the object was still traveling between the orbits of Saturn and Jupiter, a vital clue to how fast it is moving. For comparison, the Voyager probes, launched on direct paths to Jupiter, needed about 18 to 23 months to reach the giant's orbit. We know 3I/ATLAS was near Jupiter in May, is passing Mars in September, will make its closest approach to the Sun on October 29th, and by spring will again be out near Jupiter's distance. Such a rapid schedule is possible only on a hyperbolic trajectory. It is moving too quickly to be captured by the Sun's gravity, marking it as an interstellar visitor. What stands out in the TESS data is the brightness. Even beyond Jupiter's orbit, 3I/ATLAS already appeared quite luminous and kept brightening steadily over roughly 3 weeks of coverage. That is not typical for the comets we usually see. Most comets are blocks of water ice mixed with dust, rock, and gases, formed in the outer reaches of the solar system. As they approach the Sun, surface ice warms and begins to sublimate. In a vacuum liquid, water cannot persist, so the solid transitions directly to gas. This process builds the large, bright, fuzzy envelope called a coma. Water ice comets generally do not become active enough to grow a coma until they cross inside Jupiter's orbit and head toward the asteroid belt. Yet when TESS recorded 3I/ATLAS on May 7th, it was far beyond Jupiter and already brightening day by day, signaling early activity. The most likely cause is abundant supervolatile ices, such as CO or CO2, that can sublimate at very low temperatures. If it is a comet, it deviates sharply from the familiar, essentially the opposite of Oumuamua, which showed no coma at all, and unlike 2I/Borisov, which behaved like a textbook comet. By July and August, the oddities deepened, a coma formed, and a tail stretched out. But in this case, the tail appeared to point toward the Sun, not away from it, a geometry that can arise from an anti-tail effect. strong sunward jets, or ion tail distortions by the solar wind. We know the sun supplies nearly all light, heat, and energy in our system, but it also behaves like a giant fan, constantly streaming solar wind. That flow usually sculpts a comet's tail, sweeping the expanding cloud of gas and dust away from the icy nucleus to form a trailing plume, like a dog leaning out a car window with the air pushing its ears back. Now imagine the air making the face stretch forward instead. It wouldn't add up. That is why observers were puzzled when 3IATLAS seemed to grow a tail pointing toward the sun, apparently fighting the wind. To sort it out, astronomers aimed heavyweight space telescopes straight at 3I/ATLAS. Hubble, the James Webb Space Telescope, Sphere-X, the cone-shaped infrared mapper, and tests returned for a fresh look. NASA's most capable instruments delivered the clearest clues yet, but also new puzzles. The headline, "The Coma Enveloping 3IATLAS," is dominated by carbon dioxide, not water ice. Yes, there is some H2O, but the measured CO to H2O ratio is about 8 to 1, about 16 times the CO2 fraction typical for comets. The CO2 cloud itself may be immense, with a radius up to approximately 300,000 kilometers, nearly half the sun's radius, far larger than early July estimates. That scale hints the solid nucleus may be bigger than expected, too. Initial guesses put the core near 20 kilometers across, then paired to approximately 11 kilometers. But the latest readings allow up to approximately 46 kilometers. That is sizable, though not record-breaking. Several local comets exceed 100 kilometers. What is unprecedented is the extreme CO2 richness relative to water. Future observations will test whether the sunward feature is an anti-tail from viewing geometry, a jet-driven arc bent by radiation pressure, or an ion tail distortion from the solar wind making stuff up. That chemistry is essentially the inverse of what we expect in a comet's envelope, implying the object formed in a stellar system with raw materials very unlike our own. The ratios look wrong by local standards, which is why 3I Atlas feels truly alien in character. But was it built by aliens? Another odd result arrived this summer from observations with the Very Large Telescope in Chile. The VLT picked up neutral nickel in the coma of 3I Atlas, yet found no sign of elemental iron. Perplexing? Absolutely. Iron and nickel are natural companions, the most common heavy metals in the cosmos, because they are forged in stellar furnaces and hurled into space by supernovae. As a result, the pair nearly always travel together in asteroids, moons, and planetary cores. We typically encounter nickel without iron only when people deliberately separate the two in industrial processing. So how did nickel show up in a cometary atmosphere with no detectable iron? We don't have a firm answer. It's odd. Inevitably, that gap invites the popular fallback: aliens. Speculation ranges from probes to discarded hardware. To be fair, proponents aren't inventing concerns out of thin air. The data do raise real puzzles about composition, source region, and processing history. Still, extraordinary claims demand rigorous evidence. Future spectra, ionization measurements, and tighter iron line limits could show whether iron is absent, sequestered in another phase, or just masked by geometry and temperature and noise. Most hypotheses simply stretch the facts we have with a touch of conjecture. We know 3I/ATLAS brighten near Jupiter. Yes, drawing closer to the sun boosts illumination, but not nearly enough to explain the observed surge. A conservative take is early sublimation powered by an unusually high CO2 inventory. The bolder spin imagines an alien probe switching its lights on. Others suggest the thick CO2 shroud exists because a colossal starship teeming with organisms is venting exhaled gas into space. I've even seen the claim that 3I/ATLAS is a gigantic living entity, feeding on dust and gas and releasing CO2 as a biological byproduct. The curious part is that, for now, none of these scenarios can be rejected with absolute certainty. They're almost certainly wrong, but the nickel-only detection remains odd, and its cause is unresolved. Thus, an artificial origin can't be ruled out outright. Again, unlikely, yet not disproved. That urgency is why scientists are racing to capture data in the narrow observing window. In early October, the object will pass relatively close to Mars, about 28 million kilometers, still distant, but within range for a useful look. The European Space Agency plans coordinated observations with Mars Express and the ExoMars Trace Gas Orbiter, using high-resolution and color imaging to study 3I/ATLAS. We won't get postcard-quality close-ups, yet the data should separate the gas cloud from the nucleus and hint at the body's shape. Teams hope to constrain the rotation period, search for jets or fragments, and chart color gradients that reveal unusual chemistry. By late October, from Earth's vantage, 3I/ATLAS will slip behind the sun and reappear in December, already outbound. After solar conjunction, fresh photometry will track its fading and test for non-gravitational acceleration from outgassing. A final chance arrives on March 16, 2026, when it passes Jupiter at roughly 53 million kilometers. Juno remains in the Jovian system, although its prime mission was slated to end in September 2025. Planners could consider an end-of-life campaign to attempt a distant intercept. If that proves infeasible, ground and space telescopes will still follow the retreating coma for months. Each observation narrows the possibilities: comet, processed planetesimal, or something genuinely new. Answers are coming, and so are fresh questions. That's the thrill of discovery.